Hi everybody and welcome to our new video named Stochastic Models. In this video we are going to talk about Euler-Maruyama's method, a useful technique that helps us solve stochastic differential equations and that can be used as a tool to model and do forecasts of financial series. The methodology will be applied to four particular cases of its process. Just as a friendly reminder, our team is made up by Maria Garcia, Berta Lozano, Marisol Romo, and Daniela Schar. First of all, introduction, the market as a stochastic system. Within financial markets, we can find not only determinable tendencies, but also some apparently random behaviors. Because of this, we can understand the market through a stochastic process.
What is a stochastic process? A stochastic process is a system in which the states or future situations are uncertain, as they are determined not only by predictable elements, but also by random elements. Sometimes, the force of chance in the market is more influential than the deterministic aspects of it, but sometimes it is the other way around. However, it is clear that given the nature of the market, there is always a factor of risk or uncertainty regarding the future that affects all of the market's investors. This is mainly because the wealth and resources are deeply influenced not only by the actual state of the market, but also its future states. All of this has given birth to loads of probability models applied to finances. The process we will use now is an example of this. What is a stochastic differential equation? It is an equation that describes how the instant changes of a stochastic process happen. The solution of this equation consists precisely of a stochastic process that follows those changes through time. The most widely used and well-known example are the yield processes, whose general equation form is this one. As we can see, it has a deterministic part and a random part. We can find several particular cases of stochastic processes depending on the functions a and b. In this video, we will focus on understanding the usefulness of four cases to describe and forecast price series and interest rate series. First, we have the geometric Brownian movement, then the Ornstein-Uhlenbeck model, then the Vasicek model, and finally, the Cox-Ingerson-Ross model. The first two are used to describe assets and prices, and the last two are used to describe interest rates. All of these explain that a market behavior has a trend and a random force whose changes over time are represented by a random variable of a Wiener process, distributed with a mean of 0 and a standard deviation of t. Regarding its application, it is necessary to solve stochastic differential equations and to calibrate the parameters of the processes that solve these equations.
Thanks to the Euler-Maruyama method, we know that a trajectory from a stochastic process that solves the differential stochastic equation given an initial condition is this one, and it can be generated in a defined interval of time between 0 and t. We can do this through the discretization of the instantaneous changes, representing the derivative t as delta t equals to t divided by n with a tendency to the infinity. The interval between 0 and t is divided into equidistant near instantaneous partitions t0 equals 0, t1 equals delta t, up to tn equal t, and interpreting the derivative of x as delta xt equals to the difference between the former or the following value of x and the actual value of x, and the derivative of wt as delta wt equals to the difference between the following or the former value of w and the actual value of w, with h equals to 0, 1, up to n minus 1. Thanks to the properties of the Wiener process, we can interpret the derivative of wt as a normal random variable with parameters of mean 0 and sigma equals to the derivative of t. Thus, an approximate trajectory of the process is created which solves the respective stochastic differential equations through the following recursive formula. Thanks to Antonio Ruiz Moran, we have this useful table that shows the numerical equations that can generate the trajectories of the solutions of the four different stochastic differential equations of interest in this video. To double-check these results, we can use the Ito differential rule, which says that suppose x is an Ito process with the derivative of x equals to a times the derivative of t and b times the derivative of w, and let f be defined, as we can see on screen, be a function with continuous partial time derivative and continuous second partial space derivative. Then f, defined as we can see on the screen, is an Ito process, and we can obtain the equation of the Ito differential rule as we can see on screen. It is important to say that xt0 equals x0 and that this set are standard normal random variables independent of each other. Let's go to see this on Excel.
So the algorithm for the Euler-Maruyama method on an Ito's process goes like this. First, we define the parameters. For the geometric Brownian motion, we have mu and sigma. For Ornstein-Uhlenbeck, we have theta and sigma. And for Basicek and the Cox-Ingersoll-Ross, we have A, B, and sigma. The next thing we do is define the initial value of the process. In this case, we put 1 for geometric Brownian motion and Ornstein-Uhlenbeck, and 0.1 for Basicek and Cox-Ingersoll-Ross. Then, we define the upper time value t and the number of subintervals n. We normally work with the time measured in years and steps measured in days. So delta t, that is precisely the division of these two, would be 1 divided by 365. This way, with parameters and defined time steps, we can simulate a trajectory or do Ito's stochastic process described by each stochastic differential equation. Here are the results when applying the Euler-Maruyama method to each of the 4 stochastic differential equations or Ito processes. As we can see, we define here the initial value in each case and then apply the formula corresponding to each method. These are the graphs we get. However, doing a single trajectory is not enough to fully understand the solution of the stochastic differential equations. As we can see, they can change in every simulation. So we'll have to do a bunch of different trajectories to calculate its behavior on average.
By doing m different trajectories of each process, we get a total of m observations in each time point th, with h from 0 to n. In other words, by doing m trajectories, we get m plus 1 samples of m independent and identically distributed random variables from each trajectory. So this set represents the approximate distribution of the stochastic process in the moment th that solves the stochastic differential equation. With m different trajectories, we can estimate fundamental features of the process, such as mean function and the variance function. We use these estimators. These allow us to create punctual estimations and intervals with a certain safety margin about the future. Once again, thanks to Antonio, we have the actual theoretical values of the 4 models presented before, which are these ones. Now, let's go back to the Excel.
Okay, so what we did in this Excel was to simulate 1,000 trajectories using the numeric equation by Euler-Maruyama method for each model. First, we simulated for the geometric Brownian movement, and the first thing that we did was to assign values to the parameters of mu, sigma, x0, and we defined stepping time equals to 1 divided by 365. In the row 7, we can see that it's the trajectories, and in the column A, it's corresponding to the time. Here we can see that each trajectory in time 0 starts only with the value of x0, and then we apply the formula calculated by the Euler-Maruyama method. And here it's that is the previous value plus mu times the previous value times stepping time plus sigma times the square root of the stepping time times the error, that in this case, well, the error, we know that it's a normal distribution with mean 0 and with sigma 1. And then we did this 1,000 times up to the time where we reach the 1. And we calculate what will be the expected value using the formula that we already shown in the video, that in this case for the geometric Brownian movement, it is It's the value of x0 times the exponential function of mu times time, and we calculate what will be the average of each trajectory using only the function of average in Excel. And finally, we calculate what will be the deviation of every trajectory to be able to compute what will be the upper and lower bound in order to see what will be the tendency of the model. So here we have the graphic, and we clearly, before we go to the graphic, I would like to say that we can see clearly that the values of the expected value are pretty much the same as the average. So here, graphically, we confirm that thing, and we can see that here is the yellow dots are the trend line in Excel, and the red line is the average. And we can see clearly what will be the line of the expected value, and that's because it's under the average one. So we can say that it's the exact same behavior, and that's a good result. Then we made the same for the Orsten-Uhlenbeck method model. And here we have to assign values to theta, sigma, and x0. And the formula, it's this one, that it's 1 minus the value of theta times the stepping time times the previous value, plus what will be the value of sigma times the square root of the stepping time times the error. And the expected value is pretty much the same as the geometric variant motion, just that instead of mu is theta, and it's the exponential function of minus theta times the time. Here we have the graphic of this model, and here we can see clearly that there are two red lines. This one is the clear one is the expected value line, and the other one is the average line. And the dots are corresponding to the trend line in Excel, so we can see that the three of them have the same behavior. Then we did the same for the Basisec model, and here we have to define the parameter of A, B, R0, that is equivalent of X0 in the other models, and sigma. And here the formula is this one, that it's the previous value plus the value of A times B minus the previous value times the time, plus what would be the value of sigma times the square root of the stepping time times the error. And here we have this formula for the expected value, that is, if we see the parameters, it's the value of R0 times the exponential function of minus A times time, plus sigma plus 1 minus the exponential function of minus I times the time. And graphically, we can see that it has this behavior. Here also we can see that there are two red lines. The clear one is the expected value line, and the other one is the average of each trajectory. And here we have the trend line, and we can see that the three of them have the same behavior. And finally, we did all the same for the Cox-Ingerson-Ross model. And here it's pretty much the same as the Basisec model, because we have to assign the value of A, B, R0, and sigma, and the formula is pretty much the same. The only thing that changes is this multiplication of the previous value times the error. And the expected value is the exact same formula as the Basisec model. So here, graphically, we can see that also here are two red lines that has the same behavior, and the trend line that also has the same behavior as the expected value and as the average of each trajectory.
Now let's talk about the accuracy of the Euler-Maruyama method for spot forecasts. First, the margin of error depends mainly on the number of simulations M. Then, the more simulations, the higher the accuracy. The larger the variance, the less accurate the sample average is. And the large time horizons require more simulations to guarantee a minimum accuracy.
Up until this point of the video, we have used this method for given parameters. However, now we'll focus on inferring these parameters from the historical series of each of the stochastic processes. These parameter estimation methods are justified by the recursive and discrete equations given by Euler-Maruyama's method. We'll start with the least squares method. This method sees future observations in terms of present observations, since the same expression obtained from the discretization of the Euler-Maruyama's method proposes a regression model for each observation from the present observations under an error. This method also presents that the estimators of the true values of the parameters theta of the respective process given a trajectory correspond to those that minimize the sum of the squared errors of the given regression. That is, defining the dependent function of the values for the parameters as a set sum of squared errors, we get this. Now, thanks to Antonio, we have the Forer-Ito's process to make a regression analysis. Thanks to this, we can model a regression analysis in every process to estimate the parameters using the least squared method, except for the geometric Brownian movement, since it requires a trajectory transformation in a sample of independent and identically distributed random variables. Doing some algebra or simply looking up on the internet, we get these formulas for least squares.
Compared to the least square method, the maximum likelihood method consists of displaying the conditional variable as a normal random variable with the following parameters. This way, the joint probability density function can be determined given a trajectory and a determined initial point of the process discretized by the Euler-Maruyama method using the following equation, where the conditional density function consists of the density function of a normal distribution with this mean and this variance, hence denoting the likelihood function as the one that we can see on the screen. This is defined as a product of h equals 1 to n of phi evaluated in x, dh, mu h, and sigma square h, where we can use these equivalences. The natural logarithm that we already saw before provides a simple expression for the likelihood function, denotating this logarithm as the one that we can see on screen, and this is the next equivalence. The function 9 in simple words represents the similarity that an observed trajectory has according to the values of the given parameters theta. So the maximum likelihood estimators for any discretized zero process with the Euler-Maruyama method are those values of the parameters theta that maximize this function. Once again, doing some algebra like Antonio did or looking up the formulas, we get this. Using the maximum likelihood method, we can obtain the parameters for each model. So first, we can obtain for the geometric Brownian movement the parameters mu and sigma squared. For the Ornstein-Uhlenbeck model, we obtain the values of theta, and sigma squared. For the Basisek model, we can obtain the values of a, b, and sigma squared. And for the Cox-Ingersoll-Ross model, we can obtain the values of a, b, and sigma squared.
By using these formulas, we generated a Visual Basic code that gives us an average estimated value for each one of the parameters. The function receives the original parameters and simulates 10,000 trajectories with 365 time steps and saves the results in an range. Then, with the use of cycles 4, it calculates the parameter with both methods, least squares and maximum likelihood, for each trajectory. Then, we calculate an average of the values of the parameter for each trajectory and print it in the Excel sheet. Here we can see the one for the geometric Brownian motion, which calculates here the mu and the sigma, and then prints it in the sheet. Then the one for Ornstein-Uhlenbeck, the one for Basisek, where it gets a little bit more complicated since there are 3 parameters, but it's done the same way. And last but not least, the Cox-Ingersoll-Ross, that it's similar to the previous one. So the function takes the parameters from here and print them here. Here's for the geometric Brownian motion. Here's for the Ornstein-Uhlenbeck, Basisek, and Cox-Ingersoll-Ross. And here we have a table with all the results. It is difficult to demonstrate the properties of these estimators. However, by simulating several trajectories with predetermined parameters, it has been possible to verify that most of these estimators are close on average to the true values of the parameters. We can see the comparison here with this one and this one with this one. However, it should be mentioned that in the comparison of both methods, it is also obtained that the maximum likelihood estimators are more efficient, since they have a lower bias and lower standard deviation that we also calculated. The bias shows how much the simulated value of the parameter differs from the true parameter being estimated. So, the smaller the bias, the closer the approximation, and the better the method. Likewise, the standard error is a statistical term that measures the accuracy with which a sample distribution represents a population by using standard deviation, meaning also the smaller the deviation, the closer the approximation, and the better method. So this comparison can be seen here in this table, showing that maximum likelihood is slightly better at estimating than least squares method. So using these average stimulated values, we generate 200 trajectories with the original parameters, including the average, the deviation, and the lower and upper bound, with the original least squares and likelihood parameters for all of our methods, for Ornstein-Uhlenbeck, Basicek, and Cox-Ingersoll-Ross. With these results, we get the following graphs. We can see that the three graphs for each method are very similar. This is because the estimated parameters are highly alike and therefore give us similar results and trajectories. We can also see that the average, upper, and lower bound seem to be in the same levels. So using both least squares and maximum likelihood, we'll get parameters really close to reality that will help to make forecasts.
In conclusion, through this video we saw how useful the Euler-Maruyama method is. It helps us approximate the theoretical properties of stochastic processes that follow a stochastic differential equation. Even though in this video we only talk about 4 models, with the aid of some Monte Carlo principles and the law of large numbers, we can actually interpret any ethos process. Another interesting thing we did in this video was the estimation of parameters for these 4 models. To do this, we took advantage of our statistics knowledge and applied the least squares and the maximum likelihood methods. In case any of you don't remember, these methods mainly consist of reducing to the minimum the quadratic error and of producing trajectories that look like the history behavior of the series. In real life, this is useful for financial series. I don't know, for example, for prices and interest rates maybe. Now, in Excel, we were able to see clearly the tendency of each model and notice that the expected value of each trajectory was very similar to their average for the fourth. However, it is important to keep in mind that what we did in this video helped us get an approximation of the behavior of the market, but not an exact solution. Well, thank you very much for your presence, your attention, and mostly your patience. See you soon.